Yeah, because like from your room, it wasn't what room? Your room is like no, this is I didn't take coffee. I didn't take coffee. We took coffee in class yesterday. I didn't take coffee. I was sleeping. Bro. But you know it was coffee.
Alright, guys, let's begin. I'll start. So, the first thing I'm going to show you guys now is like how SumCheck is able to do reductions. Okay? So, the idea of GKR is that you have some circuits, right? Some arithmetic circuits. Now let's assume that this is the input layer. Okay? So the input layer is the thing that the verifier has access to. But then the verifier doesn't have access to all the other evaluations on the layers above, right? So the idea is that the prover is going to compute and then get some outputs, right? And the idea is that the prover is supposed to perform a reduction. That is, they're supposed to make a claim about this new layer. So let's say this layer is called W1, right? So the W1 of 0 is supposed to be equal to the output, right? That's the initial claim, for example. Then what the prover wants to do is that it wants to now make a claim about W2 that is related to W1. So the new claim might now be like W2 of 46 is equal to 494, right? But then this reduction has been done in such a way that if this is correct, the top one is also correct. And so that means that you can now forget about the top one and just focus on proving the bottom one, right? So once you prove that, that's proven. So you're good. Now, the verifier still doesn't have access to W2. Only has access to the inputs. So you perform another reduction. Then you now have a new claim about W3 of like 4, 4, 6 is equal to 21, for example. So now it has been reduced to a claim about W3, which is a claim about the inputs, which is what the verifier has access to. But then it's reduced in such a way that if this is correct, then the last one was correct. And if the last one is correct, then the top one was correct. So once the verifier evaluates the polynomial, recall the verifier does have access to this polynomial. So the verifier will evaluate that polynomial as 446 and check that the answer is 21. If the answer is indeed 21, then that means the prover did everything correctly. Does that make sense?
I thought the prover was starting from the bottom.
Huh? Yeah, we'll get into that. What you need to just know is that it's making claims. So it's saying that W1 of something is equal to something. Then it converts to W2 of something is equal to something. And W3 of something is equal to something. So this is the high level view of GKR. I want you guys to get this high level first. Yeah, we'll come again, yeah. I want you guys to get this high level first. And once you get the high level, then we'll now show how you do like the reductions and everything. But make sure you get the high level. Okay? So let's use like a proper circuit now. So let's say this is plus, plus, times, and let's say this one's are the inputs. And also we have like 1, 2, 3, 4. What will be the output here? 3, right? What will be the output here? What will be the output at the top? Yes. So the prover is saying that I evaluated this circuit on 1, 2, 3, 4. This is what the verifier knows. Okay? The verifier knows 1, 2, 3, 4. So now every layer has like the data associated with it in a polynomial. That's the W. So this one has W1 of X. This one is W2 of X. And this is W3 of X, right? So if you evaluate W3 at 0, you're going to get 1. If you evaluate at 1, you're going to get 2. If you evaluate at 2, you're going to get 3. If you evaluate at 3, you're going to get 4. Usually it's going to be multilinear, but we're doing very high level, right? What you should just think about is that there's a polynomial that represents the data on each layer, okay? Now that we have this, the prover has gone all the way up, right? And has gotten the answer. The verifier doesn't want to know what is here, and doesn't want to know what is, okay, maybe not to know the output, but it doesn't want to know anything that is like in between. Because if he knows everything that's in between, then it's almost like as if he did the computation himself, and there was no point in outsourcing it to you. So what he wants to know is like the output and the layer that he knows, right? And then when you guys do polynomial complement scheme, you won't even know this layer, but you'll still be able to do what we're doing. But you can forget about that one for now. So now, the only thing that the verifier can check is a claim on W3. Does that make sense? Yeah. Someone is going to tell you that if you evaluate W3 at 14, you're going to get 25. So if you can somehow get a claim like that, the verifier is good. The verifier knows the polynomial, you evaluate it and you check whether it's equal to what you said is equal to. If it is, then it's going to believe you. If it's not, then it's not going to believe you. So the question now is like, how do we go from here to a claim about this? Okay? So what we do is that we do a reduction. And we'll talk about the reduction next, once you understand just like the high level idea. So W1 or 0 is equal to 15, right? That's what the prover is claiming. It's saying that that's the output. But then the verifier cannot prove this. If the verifier had W1, the verifier will just check it and it's good to go. But the verifier doesn't have W1. So we need to somehow express, because if you look at this W1 output, right, it comes entirely from W2, right? It's feeding forward. So it can be entirely expressed by this. There's a relationship between the two layers. Exactly. So if you make a claim about this, you should be able to create a new claim, but that is about this, right? Because that relationship already exists in the structure. So when you say W1 of 0 is equal to 15, they will now have this dance, where they will now figure out that, oh, if W1 of 0 is equal to 15, then W2 of 48 is equal to 39. Okay? So that's like a reduction, but it's related. So if W2 of 41 is equal to 39, then that must mean that W1 of 0 is equal to 15. Do you get? So they reduce it and they make a claim about this layer. Now when they do that, the verifier still can't check that. So they need to do that same thing again. And eventually they will have a claim about W3, which the verifier can check. Once the verifier checks it, all is good. And then they are done. Does the high level make sense? It still doesn't make sense. Okay. Evaluation is up, proving is down.
Who does evaluation?
The prover does the evaluation. And the prover does the proving. Yes. This W3 is known by both the prover and the verifier. But W2 and W1 is gotten by the prover. Yeah.
So what you're saying in essence is that the prover first does the evaluation, gets the output. Then in order to prove the output, that in order to prove that the output actually came from the input that was given to the prover by the verifier, it has to like move downwards, like create a relationship from the output down back to the input.
Yes. And it's every time it's going down, it's like doing stuff. So, do you have questions? Do you have like specific? You have gotten it now. You sure? You sure? You sure? You sure? Okay. So, does it make sense? Okay. Yeah. Okay. W3, yeah. And the prover. Yes.
So now the prover proves is by calculating or evaluating these two top.
Yes.
Get the
Like,
value one.
yes, all the evaluations there.
Then the verifier now wants to verify whether they actually do this calculation.
Correctly. Yes. Yeah.
So now it does it from
The prover does it from the top.
From the top.
Yeah. Yeah.
By
So it's proving it
reducing
step by
the
step.
relationship,
Yes. Yes.
By reducing it.
Yes. But all these proofs, like all these intermediate proofs, are like trusted proofs. Like they're not complete. Because it's saying that, oh, I have this and I have this. This is equal to this somehow. Right? It's related to this somehow. But the verifier doesn't have this. So the verifier is not like fully convinced, but it's partially convinced. Then it goes down again until it's not like, yes, I can check this one fully. It's like the oracle check in some check. That oracle check is the one that will finalize it for the verifier. But all those round checks are just like partial. Does it make sense?
So does the verifier evaluate again or
No, the verifier doesn't evaluate. The verifier evaluates the last at, that's like W3 of 44 was supposed to be equal to 92. The verifier will evaluate that. If you have a very, very large tree, yes. The prover will start from up down. Yeah. But regardless of the size of the tree, like it's a binary tree, right? So the height is not growing crazily with the length of with the amount of data stored in the tree. You know, it's like log base 2 of the number of leaves. So the height of the tree is not usually like so gigantic, but it contains so much data.
So the prover is moving downwards.
Yes.
And the verifier is not actually going upwards.
It's not going upwards. The verifier is just like getting the proof and verifying each one of them. So now all those proofs are sum check proofs. Okay? Every time you go down, there's a sum check proof. When you go down again, there's a sum check proof. So your GKR proof is more like a collection of sum check proofs. Kind of. So now I want to show you guys why sum check is used in this situation. So now forget GKR a bit, then let's look at sum check. I'll start using notations because this is easier to write with notations. So if I write a notation that doesn't make any sense, just like let me know. Okay? So let's imagine we had a polynomial. Like our FABC polynomial, the famous one. Right? This is 2AB plus 3BC. This is just the polynomial. Now, what sum check does is it proves something else. Sum check proves the following. It proves that 10 is equal to the sum of FABC, where ABC comes from the Boolean hypercube. Does this make sense? Does the notation make sense? That's like 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1. You get? It's like sum. Sigma. This one is in. Is an element of or a member of a set. So like this 0, 1, 3 is like 0, 0, 0, 0, 0, 1. So then this one is not saying that ABC is from this set. So it's going to be that 0, 0, but it's written over all values. This is basically sum check, right? So sum check is that we know this is 10. Why is it 10? My people know why it's 10. On the top, this one here. Then to be an empty set. Not even 0, it's going to be an empty set. I think to be an empty set, I guess. If it is 0. But it's the math student that will know now.
If that 3 is 0,
What happens if you have a set that looks like this?
yeah, 0. And what is
What is inside? Is it just... Why is 0, 0, 0 there?
Because if it's 1,
Yeah, if it's 1, it's just 0 and 1.
Yeah, just that means a single. It's a set that has just one element.
So it's the element now.
What element
But
inside?
there's 2 inside of 0 or 1.
No, you're reasoning to the power of 0.
So I'm saying, yeah, it should be a sequence since you have 0, 0.
Is there an empty set?
Yeah, it should be an like.
No, it can't be an empty set.
Could it be empty?
It can't be an empty. What I mean, I know. I don't know.
You don't know, but it will just be
But
one
what I know, it
element.
will be a singleton set.
What is singleton
The
set?
singleton
You
set has
said that has just one element. So it doesn't even make sense in this context.
Yes,
because
because you have 2 inside.
Don't worry, we'll settle it.
We want that meat.
Let's offer you something that we feel like we know, so that we can use this as like ground. Right? Okay. Wait, let's go close to where we 0, 1, are we? Oh yeah.
Empty.
Which?
Empty.
No,
So it's a
it's not
singleton
empty.
set.
No, it's not empty. It's a singleton set. But it contains empty sets.
Yeah. That's what I'm saying. The set itself is not empty.
No, the set is not
Yeah.
It's
But
an
it's
empty. That empty stuff is still a member of that set.
So why is the empty stuff not here?
Because it's not significant.
I mean, I don't see what I'm saying. I'm
Okay,
saying
right.
about
So there should be a member of the set.
Yeah.
Remember, I think we should contain one.
Why is it not here? And why is it now here?
No, it's actually there. Look at the.
Okay, then the raised to power one.
Wait.
It's not there.
It's not there.
Raised power.
The empty one.
Raised power.
You know why it is there? Because, like, see, 2 raised to power 0 is 1. So you have to have at least 1 element.
And tell it to explain.
You have to have at least 1 element. 2 raised power 0 is 1.
Oh my god.
2 raised power 3 is 8. You have 8.
It's not the empty set. Oh wow, set.
So it's.
When n equals 0, at least
It's not
one
empty.
sequence of length 0.
You get all 3 to go.
Sequence of length
That's
0.
kind of sort of makes
What about
sense.
Okay.
Oh, I think the length.
It's-
I don't see why it's not empty.
For the 3, now each of them, the length has to be 3 elements. For 2, 2 elements. For 1, 1. For 0, the length has to be 0.
There's actually
Because-
such
that is the empty set. Okay.
one sequence. So what is doing that? The power is going to now find tuples that have that length, right? So if the power is 3, you're going to find tuples that are of length 3. If the power is 1, you're going to find tuples that are of length 1. If the power is 0, you're going to find tuples that are of length 0. And there's only one that exists. And it exists. It exists, that's why it's not null.
Yeah.
Okay. I've learned something. Who asked that question, sir? Okay. So now, this is sum check, right? Does everybody know why it's 10?
Yeah.
You remember why it's 10, right? Like it was 0, 0, 0, then 3, then 0, 0, 2, 5.
Yeah.
If anybody doesn't understand and you want me to write it, do you want me to write it? Okay. So, this is the polynomial. We want to sum over the Boolean hypercube. That's tuples of length 3. So, you know, who still remember the sequence? So that we don't have to like fully evaluate it.
0, 0, 3, 0, 2, 5.
So when we evaluate that polynomial at all these values, this is going to be the result we get. Then sum check is saying that the sum, it's trying to prove the sum, yeah, and the sum here is like, it's 10. So what sum check is trying to prove is that 10 is equal to the sum of this polynomial over the Boolean hypercube. So this is what sum check does, right? Now, how does sum check? When sum check is done, what's the last step of sum check?
Oracle check.
Oracle check, right? So we're going to reduce this sum thing here to an evaluation of the polynomial inside at R1, R2, R3, right? It should start. So f of R1, R2, R3 is supposed to be equal to some value, right? That was like the last claim sum from f of c, right? So what have we done? Now imagine this polynomial, this entire something was considered one polynomial. So I'm going to call it like f1. Okay? f1 of let's just say f1. What should I call it? It's not really a, that's the problem. Like it doesn't have any variable. Yeah, it doesn't have a. But let's just ignore it for now, okay? f1 is equal to the sum of f2 over a, b, c, right? Where a, b, c is coming from 0, 1 to the 3, right?
What is
f2 is just another polynomial that we're summing. So like f2 in this case is like 2ab plus 3bc. I don't know that. I'm trying to relate two polynomials now.
What's F1?
Two different polynomials. f1 is the sum of f2 over the Boolean hypercube, right? But now I'm naming them. I'm naming them differently. Just
Then the sum over the Boolean hypercube should be a value, not a polynomial.
okay. I know what to do. Yeah, you guys are right. That's why it had no variable. It was already constant.
Yeah.
Let's call it f of r1 r2.
No. This is how it actually is, right? In GKR, but I didn't want to like go this.
Yeah.
This is how it actually is. But my point, what I'm just trying to drive at now is that we have one polynomial that is made up from another polynomial, but it's made up in this way, right? It's made up like this is the relationship. So now we have a claim about this polynomial. So let's say someone told us that f1 of 5 is equal to 20, right? This is a claim about f1, right? I want to show you how sum check can reduce this claim about f1 to a claim about f2, which is similar to w1 reduced to a claim about w2. So when you can see how sum check does this, you'll now start seeing how sum check might do it for the layers.
That BC
Yeah,
inside 0, 1,
Yeah.
comma,
2.
0, comma 1, 2.
yeah.
Can you explain that?
Okay.
Stuff? Yeah.
So let's use GKR, right? Remember A is your output gate. Then B is your left, and C is your right. Okay? So what this F1 of A is saying is like, tell me the output of gate A. I'll draw a circuit. Please, ask as many questions as possible. Okay? Plus times plus. 1, 2, 3, 4. Right? This is what? 3. This is 12. This is 15. Okay? Now, this is gate 0. So in that thing I wrote now, let's say this was supposed to represent the GKR circuit. Let's just assume it's supposed to represent the GKR circuit. F2, is ABC.
Is that C or in bracket?
The brackets. Don't mind me. Better. Then BC in to the 2, right? So
so I understand that. So what you're saying here is a polynomial where a is alive
yes.
is equal to the entire polynomial is equal to a summation of like a polynomial where a is alive, and it's okay a b c, and a is left constant.
A is fixed, yes.
A is fixed, and b and c are
Over the
evaluated
Boolean hypercube.
over the Boolean hypercube. I
Yes.
understand that, but that square in that
Because that's been allowed for BC.
That's 0, 0, 0, 1, 0, 1.
Let's use actual values, okay? So let's say we wanted to do f1 of 3, right? That's going to be equal to the summation of f2 of 3 bc with bc in 0, 1, 2, right? Now this summation,
my
it-
concern is that two.
yeah,
and that
so
one.
what is the 2? What will the 2 evaluate to? The 2 will give you 2 tuples of length 2.
Tuples of length two.
So that's 0, 0, 0, 1, 1, 0, 1, 1,
So if it was 3, it would be 0, 0, 0.
0, 0, 1.
0,
0,
0, 1.
yeah.
Oh, okay.
So now that you have those, you can now insert it into B and C, right? So this sum will turn into like f2 of 3, 0, 0 plus f2 of 3, 0, 1 plus f2 of 3, 1, 0 plus f2 of 3, 1, 1. Does it make sense?
Yeah, I understand this. So it's just that two.
It's just
and
the
I thought
two.
that out.
Yeah, it's just like a tuple of length 2, tuple of length 3 from the field. Does it make sense? Are we good?
Yeah. So that's why this works for that oracle check.
What oracle check?
Like if you have for the last one, F3.
It means some
When you
check.
have three values,
Yeah.
you can now check the
Yes.
FC first.
Yes. So this is how you're technically like getting all your FA, FB, FC.
So what you did here basically is just what we did in some check. now.
Similar, yes.
Yes, like where you evaluate a polynomial, a partial, like you evaluate
Pass
a polynomial,
R1 to A.
keep A alive, and
Yeah.
evaluate the other two.
Yeah.
So can you relate it to? That's what I'm trying to do, like
Yeah.
relating it to
Yeah.
the
Yeah.
whole.
But right now I'm trying to show you how what sum check is doing to this structure that exists here now. So we have F1 of A, right, is equal to the summation of BC 0, 1, right? So then I have what? F2 of A, B, C. So we have one polynomial represented in terms of another polynomial. If you run sum check on this, so like the claim is going to be like f1 of 5 is going to be equal to, let's say, 23, right? This is like, imagine that this is the output node. This is like w1. w1 of 5 is equal to this. This is what the provider is saying the output is supposed to be, right?
Yeah.
Now, this output is the same thing as the claimed sum for this sum check. Does that make sense?
Okay, the output is something as the claim sum. The output at the higher level.
It's the same as the claimed sum for this sum check. Because they're saying f1 of 5 is equal to 23. So if I replace this place now with 23, it's looking like a sum check equation, right? B, C, sure. I don't want to write this every time. You get the idea. Can you see this? You're seeing the sum check. Does it make sense? So now we have like the claim about output 1. I was saying that is equal to F2. It's like this claim sum for the sum check. Now, when you run this sum check, the goal of sum check is to prove that a claim sum is actually equal to the actual sum, right? And you are saying this is the claim sum, and this is the initial poly. The thing in the middle is the initial poly. So when you run sum check, at the end of the day, you will have the initial poly evaluated at random challenges. That's going to be equal to some new value. So sum check will reduce this f1 of 5 equal to 23 to f2 of, let's say, 5 comma r1 r2 is equal to, let's say, like 900. This is making sense. No, it's random. This is the oracle check. Like at the end of the day, sum check is going to make an oracle check on the polynomial that you are summing over, right? That polynomial you are summing over is f2. It's no longer f1. So you started with a claim about f1, but you ran sum check on f2. So at the end of the day, you're going to have an oracle check on f2, which is now a new claim. And you remember the oracle check, if the oracle check is correct, then the initial sum is correct. So it's something similar. Like, we would reduce the output claim to an oracle check on the next layer. So like the output layer is W1, right? W1 of x is equal to something. But then this W1 of x is also equal to the sum check on W2. So this something is basically the claimed sum for this W2 sum check. Then when you run sum check on this sum check, you will now have an oracle check on W2 is equal to something. This was the first claim, then this is going to be the second claim. But then if this oracle check is correct, then the initial sum was correct.
You know, the output of GPR is a number.
Yeah. But you can think of it as a polynomial.
Yeah?
You can think of it as a polynomial. Evaluated at 0, for example.
That fact, isn't it the arrow already?
You know, no.
Is it not the what?
It's not the arrow already.
And you can think of maybe you can think of it as the arrow. Yeah, outside.
You know, what we give to some check
Yes.
is a polynomial of value, right?
Yes.
So now the output of GKRO is a number.
It might not be a number. Your circuit idea is restricted right now. Let me show you another circuit that is actually valid.
Okay.
Wait, just wait. This is a valid circuit. What I've just drawn now is a valid circuit.
This one has two numbers.
As two outputs.
Has two outputs. So okay.
They are
Now
not connected.
we have two outputs, right?
Yes.
Which is two numbers,
Yes.
right?
Yes.
And two numbers is a univariate polynomial,
Yes.
right?
Yes.
Which we can represent as a multilinear polynomial.
So all you just need to do that. This one is evaluated at 0.
Yeah.
You know all the nodes have labels, right?
Yes.
And this one evaluated at 1. Yeah.
Now,
In the original case, it's just like you have something that just evaluated at.
okay. Now, the way our current sum check flows is
Yeah.
it moves from a higher polynomial
Yeah.
to a lower polynomial.
By the end, it still does an
By
oracle
the
check.
end. But it still does
On the
oracle
higher
check,
polynomial.
yes. Now, from this guy now, if we are reducing back,
Yeah.
that means we are giving sum check a lower polynomial. Yes, now if we want,
What? Wait. I'm not disagreeing yet.
yeah,
I don't even understand.
okay,
Yeah.
we want to reduce, we want to verify the layer below those two guys, right?
Mm-hmm.
What are we giving sum check? Which values are we giving sum check?
By giving the output of this layer, right, which was 15. So 15 is now going to be equal to, normally 15 is equal to W1 of 0, right?
Okay.
But then you have figured out a way to express W1 of 0 as the sum of W2 of something, right?
Okay.
So 15 now is going to be the claimed sum.
Okay. 15 will be our claim sum.
Yes.
Okay.
And
so
then
that,
you are going to sum over W2 of something.
Okay, so that means, okay, I think it's beginning to make sense. So if we are getting 15 as the claim sum, then we are then passing 15 as the claim sum, and also the
W2.
polynomial below
Yes,
15.
exactly.
That's
The W,
that's
that add
why-
I, yeah.
So because that is what gave up the 15.
Exactly.
So we give some check the polynomial and give some check the
The
claim
15.
sum for it to now
Then to prove.
do other stuff.
And then the verifier will verify.
And that will just be for that particular layer.
Yes. But you know, at the end of the sum check,
Yes.
you will have a round, an oracle check
Yes.
on the polynomial you passed in,
That polynomial,
which is the
yes.
polynomial from under.
Yes.
So that oracle check is your next sum, your next
Okay, that-
your next claim,
The oracle
your
check,
reduced claim.
that the value from the oracle check is the claim sum for the layer below.
Ye- yes.
You
Yeah.
are you sure?
Yeah. Yeah.
So it's now the claim sum
For
for the
yes.
below layer.
Yes.
So you now
Not really, Shabo. Yes. Like you're on track. Like it's just details. It's just details. But I'm not expecting you to get those details right now. But yes, you're on track. So like you have the output, right?
Yes.
And then you do some check.
Yes.
Then you get an oracle
Yes.
check, right? That oracle check. The detail I'm talking about is that you have to split it into something, but just forget all those ones. So that oracle check now, is now like the claim sum is now the new
Oracle.
claim sum
Yes. That,
for the next one.
you know,
and then you
after
do that
oracle
again.
check, we are checking
I'm checking
two
that.
numbers.
Yeah,
The
checking-
final number,
exactly.
And that's
Exactly.
the polynomial evaluated at the
Yeah, yeah.
different random challenges.
Yeah.
So the value it gives to you is a whole number,
Yes.
which will now be the claim sum that I used to skip down.
Yeah. Yeah. Yeah, but the idea is there fully. You just need to now see the details. So that's where you now see how that number is divided into multiple parts and all those things.
Is the class recording?
I hope so. Yeah, it's recording. Okay. Any questions? Does it make sense? It's not supposed to make sense. It's actually not supposed to make sense. Not fully, at least. It should be abstract-ish. Yes, exactly. It should be abstract-ish. That when you spend more time on it, it starts to, you get puzzle pieces here and there.
How many weeks are we doing chicken? Calm down, calm down.
Oh yeah.
Now know the time.
No,
I don't know what is like the relationship between
the layers, right? I'll do that next. I don't know how many weeks, as fast as possible. But we're hoping 1 week and a couple days to finish understanding it deeply and implementing it. That's the goal. Max 2 weeks. If we're max 2 weeks. But 2 weeks is crazy. It's not crazy though. It took us like 1 month. It was like 1 month. But there was a big problem that the Taylor book, it explained it. Now that I'm thinking back, but we're dumb to understand. You get? So we had to like check so many different resources and everything just to reverse engineer what was happening. That was what took so long. So eventually we figured out how it works. Yeah. Yes, so we figured it out. Then we now spent another time trying to implement it. But then we figured out how to implement it. Then we now found a faster way to do it. So that's what we're now going to like teach you guys. So if you guys are taking 1 month, yeah.
What were you trying to reverse engineer?
So in GKR now, I'll show you today. But when you do the sum check stuff, you're not going to get 2 new sum checks. So it's blowing up exponentially. So what you're supposed to like combine it into one sum check. That combining it into one sum check, there are multiple ways of doing it. That's what we're trying to figure out. There was one line method and then there was one alpha beta method. Is the alpha beta method we teach you guys though?
Sorry, I have another question. For some of the individual subjects, are there cases where, like, for some of them, like, the gates are like plus and
Yeah.
division gates and
There'll be one equation that handles everything, regardless of whether it's addition or multiplication. Yeah.
Like, now, when you say that W1
Yeah.
is like because the claims of or a
The
polynomial,
the output of W1
W1
is equal to a claim sum of the polynomials at W2. Yeah.
Okay, the output of W1
Yeah.
is a claim sum that also equals to like the claim sum of
Summing this W2 polynomial over the Boolean hypercube for a particular A. Don't worry, next thing now is to like what Francis did yesterday, do like the mathematical representation of a circuit, like layer by layer. How do you express one layer as a sum of the next layer? Then once that's done, it's now start getting clear like why it's a sum check. Why it's a sum check. Any question? Yeah.
let's continue.
Let's continue. This I guess dicey. This I start getting dicey. Oh. Okay. So now I want to create a mathematical representation of the circuit. Like convert the circuit into maths, right? What you guys did yesterday. What Francis made you guys rediscover yesterday. So you have a circuit like this. And then you have your inputs. Then let's say this was plus times plus, right? This would be 3, this would be 12, and this would be 15. The next layer always comes from the previous layer, right? Like this layer, this 312, came entirely from this and those operations there. There's a yeah. I like the values here. No, sorry. The values here came entirely from the values at the bottom, right? Like the 3 came from 1 plus 2, and then the 12 came from 3 times 4. So there has to be an equation that encodes that transfer. And yesterday, you guys figured out what that equation was, right? So it was right? Don't worry. ABC. So now, every layer has a W polynomial. That W polynomial just represents the evaluations at that layer, right? So we have W1. Let me now start using the labels because it's now getting important. Okay, so W1 of X, right? Just one bit. So if you put in 0, it's going to give you 15. Does that make sense? And this one is W2 of X also, right? While this one is W3 of X, Y. Does it make sense why XY? Because the labels are 2 bits each. So 0, 0 will give you 1. You can make it X1 and X2. Why do you want to make X1 and X2? Okay, let's make it X1 and X2. No, it's not invariant. It's still huh? It's fine. Just X. But I can make it X1. Huh? We can also use A, okay, use B. It's just a variable.
It's just one value regardless.
For which one?
So if it is S, it's showing that one being
For W1. And why is there x1 there?
Why is it X? Yeah.
Because of no, it's still going to take. You're going to there's something called multilinear extension, right? So like you take a value or an array and you extend it into a polynomial that you can evaluate at any point. Because right now this only has like let's say like evaluations for 0, 0, 0, 1, 1, 0, 1, 1. But you might want to evaluate it at 4, 5, right? So you do the MLE, which is what you guys have already done with multilinear polynomials. Multilinear polynomials is like when you take in the evaluation form, you are now like a multilinear polynomial is now a multilinear extension of that array, because now you can evaluate it anywhere with all your pairing index and everything. That's how you're doing like the multilinear extension. So you're extending the domain you can evaluate it at. Okay. So what is this add I doing? Let's start there first.
Checking for addition
I know anything.
Yeah, it's checking where the addition, like where the addition gate exists. So it returns either a true or a false.
Yes. There is either a 0 or a 1,
Yeah.
depending on the configuration. So you're going to pass it a configuration, right? You're going to say, I have an output at label A. That output has a left node at label B, and it has a right node at label C. And not just that, label A is an addition gate. That's what add I is doing. The mul I is saying I have an output at label A, I have a left node at label B, and I have a right node at label C, and the output node is a multiplication node, right? So two things must be satisfied. The connection between A, B, and C must actually exist in the circuit, and the A gate must actually be the operation. Make sense? So the goal now is like this W1 we want to represent it as some function of W2, right? That's the goal. Once we want to represent W1 as something that only contains W2. That way when we run some check, the oracle check will be only on something that contains W2. So I think I'm just going to write the formula. There's no need to derive it again today. So
I think say want to present what as something that contains W2.
want to represent any output in W1
Okay.
as a function of W2.
That's a reduction now.
Yeah, that's like showing the relationship between the two layers,
Yeah.
right? Because if you look at it, any output of W1 can indeed be represented as functions of W2, right? Like this 15 now is represented as 3 plus 12. That's indeed all from just W2. And then this 3 is represented as 1 plus 2, which is just from W3, right? So if we know how to do it visually, then there should be a way to do it mathematically.
Okay.
So what we need to do is that we need to find the gate. So we'll be giving the output label. So let's say we're giving W1 of 0. So we want to find a formula that when you pass in W1 of 0, it's supposed to give you what? But it's only supposed to use things from W2. Right? So how will it do this? What it's supposed to do now is that it's supposed to find all the wires that go into that 0 node. Because there's no reason why it's like this, right? The node could have literally been like this. Like you could have had a node connection that's like this. And maybe there was one other node that was just like there. So it's not always like, oh, it's always be 0, 1. So that means you need to do a search. And then your add I will not tell you whether you have found the correct combination of wires or not. So that's where the add I MLE comes in. So we need to search over all possible combinations of labels. So we know that the output node is a single bit, left is also a single bit, and right is also a single bit. So that means that we should be able to try every possible combination of 3 bits, and one of them will correspond. And once we find the one that corresponds, add I will tell us that that's the one that corresponded.
Sorry, sir. Why is it 3 bit? Is it because ABC?
It's because of A is supposed to be the output, right?
Yeah.
How many bits is that? Then B is supposed to be the left, right? 1. And this one is supposed to be the right, 1. So A, B, C, 1, 1, 1.
But the B would be like, the answer will be changed.
What do you mean B and 2 will change?
No, it's just one.
Okay, it will be 1, 1, 1. Okay. Yeah, yeah.
I don't know if...
Actually thought of it as in, I was thinking something like an iPad queue where we need to
Yeah, you will do that.
do that.
Yeah. Because the only way we can search... No, what we're trying to do, we're trying to search all possible wiring
Okay.
that can enter into 0. Right? Since we're looking for all possible wirings that can enter into 0, we need to search the entire space of left-right nodes. Yeah, you know the output is already fixed. We already know that, okay, we want to evaluate at 0, right? So we need to now search all the possible wires. That is all the possible lefts and all the possible rights. And we're looking for the one that is actually in the circuit. So the add I and mul I tells us what is in the circuit already.
So they're like evaluating add I over 0, 0, 1, 0, 1, 0, 1, 0, 0.
Yes, but
So
you are fixing the outputs. So remember that the add I is like add I ABC. The A is the output, right? So you already you're trying to evaluate W1 at 0. So you already know that the output node you're looking at is 0. So that A is fixed to 0. Then you're only like trying B and C until you find a matching left and right node. Then once you find that, add I will give you 1. And then it's not do the actual addition. But then so the multiplication node, add I will never give you 1, regardless of all the left-right nodes that you try. But then mul I will give you 1 for some combination of left-right nodes. And then you now do the actual multiplication.
sorry, sir, for this now,
Yeah.
I don't know if it is the 0 one that is confusing me. Like we have add of like 0, like add of 0,
Yes.
0, 0, 1. Like this one.
Out of 0?
Like 0, 0. 0 as the output.
Yeah. 0, 0, 1. Yeah.
So we also do for another combination. Add of let's say 0, 1,
1,
1.
yeah.
That one is 0.
Yeah.
They will be for all.
Yeah.
and all, right?
Yeah. So let me write out the equation now. So this is add I of x1, so that's fixed, right? It's like we're saying, what is W1 evaluated at? So this is fixed. So what we're now doing is like we're iterating over BC. And then once we find a match, we want to add it, right? And how do we add it? We go down to W2, we evaluate at B, plus W2 evaluated at C. Remember that B and C are the labels of the left-right. And the left-right is inside where? W2. So that's why we need to evaluate W2 at B and C to get the actual concrete value, which is 3 and 12 in this case. Then we do plus mul I of what? X1 also, right? BC times W2 of B times W2 of C. But this is not complete because this is not searching, right? In order for you to search, you need to be trying all possible combinations of B and C, right? To try all possible combinations of like the nodes. So that means we need a what? So W1 of X1 is equal to the summation over BC in 0, 1 to the 2. Does it make sense? Does it make sense?
Yeah, to an extent.
Are you sure?
Yes.
It's not supposed to. So, to an extent, yeah. Slowly but surely. So this polynomial that is inside here, we call it the FBC polynomial. FBC polynomial.
FBC.
BC.
Is it because of BBC or just generally?
We call it the BC. That's like the A has already been fixed, right? So like I partially evaluated that FABC at A. So I just left to BC to sum over the Boolean hypercube. Yeah.
But this equation now, this particular equation now, is just for one layer.
This is the equation that
For
handles.
the W2 layer.
Yes, this one is for W1 relating to W2.
W2.
But that's because I made it concrete.
Yeah.
Right, I wrote
But-
one too.
But this equation now will change if we are going lower.
Yes.
So if we are going lower, that 0, 1, that set of 0, 1 to square
Might
will not
increase.
square anymore.
Yes.
It will be like
4.
4,
Yes.
right?
Because B here, remember B here is 2 bits, right? And C is also 2 bits. So that means that the B, C here are all going to be 2 bits. So you need to search over 4 bits. 0, 0, 0, 0, 0, 0, 0, 1. This is why I was saying that your transcript, you need to squeeze. When you squeeze multiple times, it should be changing. Because of, in some check, you're going to like get a challenge for B. But B could be 2 bits, which means that you need to get 2 challenges. So your transcript is not changing. Every time you pull a challenge twice, it will still be exactly the same thing, which is problematic. Okay, I'll also stop. So this is a point in the layer above, represented as an equation of the layer below. Yes. So it's a point, then represented as an equation of the next layer. Just for the next layer. No, I don't get. Wait. You said x0. Okay, W2. Yeah, 0. You mean like if we said W2 of 0? I don't know if I get your question yet. I don't think I get your question yet. Alright. Any other question?
So if you want to get W3 now,
Yes.
can we squeeze, like when we get it in terms of W2, like we get W2 of X, X1 perhaps is equals to summation of BC in what? 0, 1 raised to power 3. Is that not?
Are you trying to express W3 as W2?
Yes. Is that what we are going to do?
I think it will be 4, right?
Okay, if then we have an input.
No, I mean like the 3 that I talked about was like 0, 1 raised to the power of 3, right?
Sorry, raised to power 4. Right?
Yeah, raised to the power of 4, yeah.
So we will now put it in W1.
No, W1 is not related again, right? Like you went from W1 to W2.
Yeah.
Then you forget
Can we
about
go from
W1.
W1 to W3.
Technically you could, right? But it would be explosive.
Yeah, that is what I'm asking.
Yeah, but that's not how you would actually do it. Yeah. Well, if you go from W1 to W2, you get two sum checks. If you go from W2 to W4 without compressing, you will now get four sum checks. So that's problematic. So what you want to do is you want to go from W1 to W2, get two sum checks, but convert it into just one sum check. Then you now go from that one sum check down to two sum checks again. Then you compress it into one, and then you just do something like that. What will be the next course of action now? I think we should create this polynomial, right, for a circuit so that we can test it out and see if it actually gives us the output at that layer. I think that's going to be the best. Okay. I would like us to create it for this one, right? Because the other one is too simple, right? It's just one output. So this one we'll be able to test it on like two outputs.
I think what we tried to derive yesterday was this formula.
That's why I'm just giving it to you straight. All right. So let's express.
We have just two.
Because we have just
Because
two
we have two gates.
gates. So what you just independently discovered is that you can have more than two gates. They call it custom gates.
Or if it is like subtraction and
That's a yes subtraction now.
division,
Yeah.
can't you just use like that addition? Just I don't know what I'm thinking. Yeah, probably multiply by minus one or something. Do you get what I'm trying to say?
Well, if it's like if it's like a gate now, let's say like you didn't just have plus and multiplication, but you had, let's say, plus, multiplication, and subtraction, or division, or exponentiation. What you can now do is that you could write another, right? Then this one will now do the operation. For example, you get. So it's always like something that will check the gate and then do the gate operation. It's like check 0, check 1, but not for check add, check more, check exponentiation.
But GKR is always having addition and multiplication.
Because every computation can be expressed as addition and multiplication. That's why they did it this way. So that way you can now, once you know that it works for addition and multiplication, then you know that any computation can work. But depending on the kind of computation that you're actually doing, there might be better gates that you can use for that computation. Do you get? Like if you're doing machine learning now, I'm sure you have like more custom gates. There's this company Expander. Yes, Expander. They're doing like GKR based stuff. So they changed it from like just add and they removed the add entirely and then just left more. But then they are achieving add through just like interpolation. So it's very flexible. The goal is just to like really understand the structure deeply and then you can just play around with it. Like yesterday we slept by till 6 in the morning. So except to see my work over like 7. So I'm running on like 1 hour of sleep right now.
Wow.
But just because we're like exploring GKR, like just the circuits representation. Like there's still a lot. Okay, so that was now. Let's create oh, now this is a good chance to use this other. Okay, let's get these polynomials. So what we want to do now is we want to represent W2 as a function of W3, right? That's the goal. So we want to create an equation that when we pick any output of W and we run it, we'll get 3 or 12, right? That's the idea. So if we wanted to express W2, W2 will be what? W2 will be equal to the sum, right? Right? Of BC in what? Raised to the power of what? Is it 2? Is it 3?
Sorry, in form of W3.
4.
4. Yeah.
Do you know why it's 4?
0, 0, 0, 1.
So it's 4 because of it depends on how you want to do it, right? You saw the way I wrap BC in a tuple. It means that this power here should be for the total, BC total. So this, in this case, that will be 4, right? So I'll have like 0, 0, 0, 0, on and on like that, right? But then there's another way to do it, where I'll just write BC without Z. But then I now say they should both be in like 0, 1 to the 2. So what I'm saying now is that B should come from this, and C should also come from this. You get? So B in this case might be like 0, 0. Then C will be also 0, 0. It's still the same. It's just like different ways of writing it, right? But the reason why it is 4 is because of the left is 2, and the right is also 2. So in order for me to iterate over all possible left-right values, I need to iterate over all possible 4 value combinations. Does that make sense?
Wait, that means it's. Oh, okay. 0, 0, 0, 0. Where each of the 2 bits are mapping to like the
Left and right. Yeah.
I write it as being 0, 1, 2, 0, 1, 2.
Yes, you could. You wanted to say something?
But then for the previous one, you didn't use square.
For the previous one, use square.
Okay. Is this guy head then?
Does it make sense? No?
How will you like evaluate? How will you know that okay for this particular layer is 4, for the next layer is
That's an implementation detail. Right now, you just look at it, right? And you can see that it's 4. Okay? Don't stress yourself too much. Yes, it's entirely related to the number of. But the one we're doing right now is like you have 1, then it becomes 2, then it becomes 4. So it's always like increasing.
So can you write what it looks like when it's 2 and what it looks like when it's 4?
When the B come and say
When they are like when it's 0, 1 is called 2 and 0, 1 is called 4.
0,1 raised to the power of 2 is just 0, 0, 0, 1, 1, 0, 1, 1. Then 0,1 raised to the power of 4 is 0, 0, 0, 0. I'm not writing everything on.
Alright, yeah,
So
Yeah.
you just all the possible available.
Yes, all the possible elements in the Boolean hypercube.
Are we going over all of them?
Yes, we're going to all of them.
In this tree now,
Yes.
there's no 0, 0, 0, 0.
There's no 0, 0, 0, 0, 0. Right? Is that what you said?
There's no 0. The 4 zeros, is it from W2 or is it just W3?
So,
Based on the
let me write out the full equation first. Yeah? Yes, this 4 0 is based on W3. Yes.
But there will never be a 0, 0, 0, 0. Are you saying that it is a possible tuple or every tuple is considered?
The same thing.
No. In this tree, there's no, like on the 1, 0, 1, 1, there's never going to be a 1, 0, 0, 0.
And now guys, on the 1 0, where's 1 0 1 1?
To the left,
3 4, right?
Yeah.
Yes. So yeah, that's this tree. Right?
Okay.
We're trying to create a formula that works with any tree.
Any possible tree.
So because of the fact that the formula cannot see the tree that you have drawn, it needs to try all possible combinations of input outputs, right?
Right.
So the add I and the mod I is the thing that will not tell it that in my own trio, I have that.
Okay. 2. This 1011. What exactly is representing?
10 is representing B. So if it tries 1011, it's saying that I'm guessing that you have a left node that has label 10.
And what is that label?
The label is the. So this is like. So
Yeah, but like what is it?
only what is it? It's binary, it's bits.
But 10 is not 3.
No, 10 is not 3. 3 is the input. 3 is the actual evaluation. So you have like 4 nodes on the input layer. Each of those nodes has a label. The label is entirely dependent on the order in which you see them, right? So forget about the things that are inside.
Okay, so essentially, there's a possible tree where there's this plus plus, and then that leads to other nodes.
And even you can have a tree where, like, I'm just drawing from the second layer, like, you can have multiplication here. But then this one, this node here, goes here and here.
Okay.
And then you have this other one here that goes here and here, right? So this is 0, this is 1, this is 0, 0, 0, 1, 1, 0, 1, 1, right? So the add is actually 0, 1, 0, 1, 1, right? This is what will trigger to 1. But in this other one, the add is 0, 0, 0, 0, 1. This is what trigger to 1. But the equation is not supposed to know this. So the equation is supposed to try all possible things. And then your add I MLE and your mul I MLE will tell it whether that fits your current circuit.
So at what point does, I'm clear on that, at what point does the 0 and 1 of W2 enter this formula?
The 0 and 1. This one here, right?
Yes.
So this is now like the A.
Okay.
You get. So you fix A. And then that fixes A all in all these places. Then you now try all possible.
I
So
think
like
it's just like that Lagrange basis now.
Don't confuse me.
No, like that L, like the L.
Yeah, there's a relationship.
I get
The add I and the mul I are like check add, check mul. So if it's add, then it will be a 1. If it's not add, then it will be a 0. But it's doing more than that. It's doing more than just checking the operation. It's also checking the left and the right labels are correct, right? It does 2 checks. It checks that if you do like add 0, 0, 0, 0, 1, right? It's going to check 2 things. First thing it's going to check that the label, the gate at 0 is actually an addition gate. That's this one here. But then it's also going to check that that gate, the left node is 0, 0, and the right node is 0, 1. So you're going to make those 2 checks. If those 2 checks pass, then it will now give you a 1. You don't confuse yourself. Right?
So if you are
No, I thought you were mapping the outputs with the inputs. Like I thought we were doing the output. So, okay, that's 0 now. That's 0. Is it for
That's the output.
operations or for the outputs?
Which 0?
the first one.
Like
This
for
0.
The, for the W2 layer.
This 0, right?
No, like from W2 layer now.
It's for the node.
Is it for the operation?
It's for
like
both.
Plus or for the output?
For both.
It represent okay.
It's just like a node has an operation and a value. There's an operation and an evaluation.
Yeah.
But except for the inputs, that just has like evaluations.
Because if this W2 now, if this tree now has 4 layers,
Yeah.
W3 now counts
3.
operations.
Yes, yes.
And then you
You
now
have like operations
for
here.
the
Yes.
node and for the-
Yes.
so that means there will be, from what I'm seeing, if it's like the tuple to power of 2, right? Like we said now.
Okay. 0, 1, 2, 4, so yeah.
That means it's going to be it's going to be a summation of 4, because it's the combination of 4, right? It's going to be a summation of 4 different combinations
What do you mean?
Like, you know, what you did is you're doing check add and check more for each combination. Like
For each combination of output left,
each
right,
combination of output and
left,
and BC now.
and BC, yeah.
You understand?
But output is fixed, right?
Yeah, output is
So you're doing combinations of BC. Yeah.
And BC will have 4 combinations.
For which one? W3?
For no, for W2.
If it's W2, then BC is just like B is 1 bit and C is 1 bit now.
So it will be 0, 0, 0, 1, 1,
Yes.
0, 1, 1.
Yes.
That's
For
combinations.
yeah.
So now that means it's going to do check add and check more for each combination.
Yes, for each of the 4.
Check add and check more for
Yes.
each combination.
Yeah.
So it's going to repeat that for the 4 combinations.
Yes.
And that is what is summing, right?
Yes.
Everything.
So only one combination, right,
yes.
would actually output 1.
Yes.
And that's the only time it's not going to do the actual
The actual
multiplication or addition, depending on which one.
okay,
Is.
out of the 4
Out of the 4
combinations,
combinations, only one will be valid.
That means if we are going down to W3, it's going to move down to like
8 combinations.
8 combinations.
Yes.
And out of the 8 combinations, 2 will be valid.
Depends on the gates. If you're let's say like you're trying to get the output of 0,
Yeah.
only 1 will be valid.
Okay.
Only when B is 0, 0
Yeah.
and C is 0, 1
Okay.
will it output 1. And only at that point will you now do the addition of 2 and 1
Yeah.
to give you 3.
Okay. But in this case now we have 2 gates.
You have 2 gates.
So it's only 2 outputs, 2 combinations will be correct.
Yes, 2. Not necessarily like 2. You know you're always fixing the outputs.
Yes.
So you either choose the output as 0
Yes.
or 1.
Okay.
And once you do that,
Yes.
that limits your left and your right.
So it's still only one.
There's still only one that will be correct.
Yeah.
So if you fix output to be 1,
Yes.
then only when B is 1, 0
Yeah.
and C is 1, 1 will it actually do any computation.
Oh.
Not even though it's like B is 0, 0 and 0, 1, it won't work because the mol I would
Yeah.
say no, this doesn't work.
Okay. So in this case, it's going to split it. It's going to split.
Yeah.
In this case, it's going to split it now. Like the output, it's going to split the output because here now there are two outputs in like the W3.
Uh-huh.
There are 2 outputs. So it's going to do for 1 output and run. Will it do for 1?
You're creating an equation that can give you any of the outputs.
Any of the outputs.
Yes. So you just need to pass it the output label.
Yes.
And then once you pass in the output label, if you pass in 0, to give you 3.
Yeah.
If you pass in 1, it's to give you 12. So, but it's just one equation at the end of the day. So we're trying to do that now. We're trying to get that equation that when you now like put in the correct output label, it will give you the correct output evaluation.
I'll say if you put in 0, 0 and 0 1, it give you 3. If you put in 1, 0 and 1, 1, it give you 2.
You're not the one that is going to put in 0, 0 and so we're creating a function that relates evaluations here to inputs here. Okay? So you're going to ask that thing for what's the evaluation at 0 or what's the evaluation at 1. Then it will be the one that will do like the search over the Boolean hypercube for you. So you won't need to do all this, you won't care about this. Only if this one had like further down, right? And then you now created a polynomial that shows the relationship between these two. That's when you can now ask that polynomial, what is the output at 1, 1? Then it will now come and search down for you also. Does it make sense? Every question should be increasing everybody's total understanding by like 1%. Yeah?
Our BC,
Yeah.
is it going to be like a particular combination of 0 and 1 or all?
You will try all possible combinations of 0 and 1. Because the formula doesn't know how your circuit actually is. Right? So it has to try it and then test it against the add I. So the add I and the molar is the thing that actually knows like your specific circuit. How does it look like, right? Because you're going to equate the add I to 1 where there is like a output left, right, and it's valid. You will insert it in your add I and molar at those. Yeah, you'll have hard coded that, exactly. So the adder and the molar is like your circuits. That's your circuit. But then the GKR formula is just saying, give me any add I, give me any mol I. I will now use that to help you talk about different layers.
So all of this are using look to do the searching.
We don't know yet. That implementation detail. Just focus on understanding the key idea. But yes, most likely this will be using loops. But you already did that in some check now, like summing over the Boolean hypercube. Don't worry, implementation detail. When we start implementing, figure that out.
So that means whatever stuff we are coming with, once you give it 0, like once you give it 3.
Are you talking about a formula that relates W2 and W3?
Yes.
Yeah.
So whatever formula we are coming with,
yes.
Once you give it
0,
3, as that 3 now value 3, that is at 0.
So you're not giving it the value, it's the one that will tell you the value. You're giving it the label.
The guy down now.
No. Wait. We're creating a formula that can express W2 of X as W2 of X is going to be equal to some formula that only uses W1, right? So if you now evaluate W2 of 0, the answer you're expecting is 3. But it only got that. You know, normally you could have just like looked into W2, which already has all the answers, and then said, okay, what is W2 at 0, which would be 3. But now we're trying to get that same 3, but using just W3. Sorry, this is supposed to be W3, not W. So we're creating a formula that expresses W2 entirely with W3. Then when you evaluate that formula at 0 or 1, it will make use of this W3 to help you get the value at that point. But then to do that in a sum check E way, right? It's so that we use sum here. This is the formula technically, but we use sum here. So this means that when you run sum check on this formula, you are now going to have claims about the thing inside, which is claims about W2. So you had a claim about W1 to start with. When you run sum check, you got a claim about W2. And sum check is like the glue. It's the thing that allows you to do that reduction. So now you can forget about the W1 claim and just focus now on the W2 claim, which is now the same thing as like you're starting all over again, but you started at W2. Then you now do the same thing, you get to a claim about W3. And then that's now the input layer. Now the verifier can actually check that claim. Let's build it now. Okay. Don't worry, you guys will get it. Huh? Yeah. Yeah? Yeah? Notation. Okay. Yeah. Yeah, the trying to use W3 to get W2. Values in W2, yes. So you're checking if, like what we're doing right now is like we're trying to create like the relationship in the first place. That's like that W2 of X should be equal to something using W3, right? So at the end of the day, those two things are supposed to be technically equal. But that equality is like claimed sum for sum check. Yes, the evaluation of W2, let's say 12 or 3, will be the claim sum for something in W3. Then once you have that, and you run sum check, you get an oracle check on W3. That will now be like your new... Yes, so you start here, you go here. You start here, you go here. But when you get to this one, the verifier can verify themselves.
So is it more like we are doing a reverse of because now we are going from like 16 to 1, and now we are going from 1 to 16 back.
Why is 16 to 1?
Like 16 data in an array to 1, and now we are going from 1 to 16.
Not, I think it's talking about absorbing.
Yeah, like
and then
we are going from 16.
So what Fiat Shamed does, Fiat Shamed turns public coin interactive protocols to non-interactive protocols.
No, I'm not talking about whether it's interactive.
Wait.
I'm talking about the.
I'm telling you the job of Fiat Shamed. That's where it applies.
So what I'm saying now, like, is it like the reverse of what we've been doing?
No, it's not really. But then I don't know how to explain to you that it is not really. You're not here, right?
No, I get the concept such that.
What do you know about this?
At the end of the day,
yes.
The verifier knows
this one, yes.
the bottom layer. The prover is
evaluates it.
Now he's going to go through the work of getting that one, getting the next, equating it to the next layer. Once he gets the next layer, like whatever result he gets from this will be equal to the one that the prover gives to him. Then he will use the result from this layer to get the one from the next layer, and he go down like that till he gets to the one he knows. Then he will be able to verify that whatever was coming from the top is actually true.
Yes.
So I get up.
Your question maybe on a very philosophical level.
Yes.
You can say that there's a tiny string of relationship, but not really. In like a practical or pragmatic or
So then now the next question is the positional knowledge of knowing where the plus or the multiplication is.
Yes.
And stuff like that. Like how do we go about knowing that
so
we're going to have this sign here?
You encode it into your. So when you're writing your circuit, technically like writing your adder and molar is like technically like this gate now has a unique name. The name is 001.
Okay.
Right?
Yeah.
Like output. So 001, but it's an add, right? So imagine like having like an add array and having a mul array. So in the add array you just put 0, 0, 1. And the mul array is just empty. For example, this can represent just like layer 1.
From yesterday's class, that one at the top is 0, quite alright.
Yeah.
The one, the W2 is supposed to be like 0, 0, 0, 1. And then the
wait.
0, 1.
Wait.
0,
You want to use as few bits as possible to label these guys.
Okay.
So usually you should always try and label it with just 1 bit. Okay? So this one it's doable with 1 bit, right? This other one is doable with 1 bit.
Yeah.
This one is not doable, right? Because we do 0 and 1, there's nothing left. So you need to do 0, 0. But you can just figure out instantly by doing log base 2 of like the number of gates.
Yes.
And then you know how many bits. So this one is fine like this one. Make sense?
Yeah.
Cut up? Okay. Let's now build the W polynomials, okay? So if you want to build W1,
While you were explaining to us, you said when you want to get the last polynomial,
the last
you
polynomial.
can equate it to any one of these 3 or 12.
No, so you get a general formula that relates W2 with W3. But then you can now use that formula on either 0 or 1. So if it's on 0, then the answer will be 3. If you do it on 1, the answer will be 12. Does that make sense?
I'm talking about the one that you input this 1, 2, 3, the last one.
Mm-hmm.
Into.
That's like, it's going to be, what do you mean input into?
You know there will be a formula.
Yes.
You input 1 and 2. It's supposed to give you, in the add, what you call it? The add whatever, it's supposed to give you the output for that particular gate.
1 and 2?
Mm-hmm.
No. You don't input, so your inputs are usually the labels,
Oh, okay.
not the concrete
Yeah,
values.
so like that particular polynomial,
Mm-hmm.
you were saying that you could equate it to either 3 or 12.
So, I don't know how best. So there's a polynomial here, right? Called f0 of BC. No, sorry, f0 of, let's say f0 of A. If you raise polynomial at 0, you're going to get, but to make use of 3 and 12 under the hood. Then here also, there'll be another one, let's say f1 of A. If you raise it at 0, you get 3. But it's going to make use of 1, 2, 3, 4 under the hood. And if you raise it at 1, you're going to get 12.
And these are invariant.
Yes. Then it would make use of those ones underneath. But then you don't need any other one here, because there's nothing down anymore, right? Unless you had like another layer. But I'm not sure I got your question fully.
I also didn't hear like that's what I'm trying to like.
Okay. But just like if it comes up again, just let me know. They are not necessarily univariate polynomials. Because of in this one is a univariate polynomial, right? Because the A is just 1 bit.
Yes.
This other one too is a univariate polynomial because the A is just 1 bit.
So because
But when you go down here now, this f2 of A, this A is no longer 1 bit. It's now 2 bits. So it's no longer a univariate polynomial. It's going to be like f2 of A1, A2. Something like that. But let's move.
But then, just a quick one then.
Yeah.
Does it mean we are working with the binary indexes or and not
Yeah.
with the values exactly?
What do you mean? We're working with both. What do you mean working
like
with?
Is it like we are working with the 0, 0, 0, 1, 1,
And where are we working?
Like if we are imputing the values into this, like if we are creating the formula.
So that f polynomial now
Yes.
takes in the binary, the labels.
Takes in the labels.
Yeah. But let's just build it so that we can actually see how it works. So the first step we need to do is we need to build out the W's, right? When we build out the W's, we need to build out the add, then we need to build out the mol. Then once we have add, mol, W, we should now be able to combine it to build out that FBC that relates two layers together. Okay? Our focus is these 2 layers because it's more interesting. Like we can test at 0, we can test at 1. So now let's build W2 of x1, right? This is just a multilinear polynomial that when you evaluate at 0, it gives you 3, and when you evaluate at 1, it gives you 12, right? That's check 0, check 1. Okay? So W2 of x is equal to check 0, which is like 1 minus x. That should give you what? 3. Plus check 1, which is x times 12, right? So this is going to be 3 minus 3x plus 12x, which is equal to 9x plus 3, right?
Yeah.
This is W2 of x. If your is at 0, you get 3. If your is at 1, you get 12. Cool? Next up is we want to build the polynomial. So next up is W3. Now this one has 2 bits, right?
Yeah.
So we now have to do it like one by one. So let's call it x1, x2, right? So I'm just going to write it like in the check form, right? So it's like check 0, 0, right? Should be multiplied with 1, right? Then check 1, 1 should be multiplied with what? 2. Then check. Is this making sense?
Sorry, how did you get 9x plus 3?
I interpolated this 3 and 12. I'm trying to create a multilinear polynomial. That when you evaluate to 0 is to give you 3. And when you evaluate to 1 is to give you 12. So evaluating to 0 means like check 0. Remember check 0 is 1 minus x times 3. Then check 1 is just x. That's x times 12. So you now multiply it out and then you get 9x plus 3. So you can see if you evaluate at 0, 9 will disappear, right? So you have 3.
How we get the polynomial at the lower level?
No, this is just the polynomial that represents this layer. But so this is W polynomials.
Yeah.
So we're doing the W polynomials first. Then after we're done with this, we'll do the add polynomial and the more polynomial by hand. So we'll have the add, more, W2, and W3. Then when we have this, we can now write out this equation here. So that we can now have the formula that can give us any output of W2, but it will use W3.
Is that an actual step?
This is how you would do it, yes.
Like,
But we're doing it by hand.
no, like that interpolation is an actual step to get the polynomial.
But it's like you're creating the multilinear extension. You already have like a multilinear polynomial library, right? That you can pass in the evaluation form. It's like what I'm doing. But me, I'm interpolating because I don't want to be working in evaluation form. Like you don't need to do that interpolation because you already have something that works over evaluation form.
Yeah.
But just to make things simpler for myself, I'm doing it over correction form. Does it make sense?
And this, when we're done with the W
Yes.
polynomials and the other more, this W and X1 is what the prover sends.
No, it doesn't send it. But I've not even started talking about proving yet, right? We're just talking about like relationship between layers first. This one, yes. We're going to create something that, we already have W1, X1, which is the thing at the top here, 15. So we're going to try and create the same thing by using W2 alone.
All of this now is just W2 or is W2 and W3?
All of this here is W2 and add I multi. But when you like simplify everything fully, you are technically supposed to get back this W.
So if it's in check 0, check 1, how do you come about the checks?
Is that multilinear polynomial interpolation? It's like Lagrange interpolation but for multilinear polynomials. It's like the. What do you mean? No, it's just binary. We're only working over Boolean. So just check 0, check 1. It's good. You guys keep asking your questions though. It's needed. Just once anything is not clear, just ask. Okay, so let's just do this straight. What's check 0, 0? 1 minus x1, right? 1 minus x2 times 1, right? So we're done. Then this one is check 0, 1, right? So that's 1 minus x1, x2 times what? Then plus x1, 1 minus x2. You don't get it. What do you mean you don't get it? So 0, 0, right? It's supposed to evaluate to 1. And we're creating a formula that has x1, x2. So 0, 0 means that x1 must be a 0 and x2 must be a 0 before we should get out to 1. Okay? If x2 is a 0, we can check for that by 1 minus x1. Sorry. So if it's 0, that will be 1, right? And 1 minus x2, if x2 is 0, that will also be 1. So 1 times 1 is good. 1 times 1 is good, right? And to give us the output. Now let's look at the other case. We're expecting x1 to be 0 and x2 to be 1. So if x1 is 0, it will be 1 minus 0, which will give us 1. And if x2 is 1, it will be 1. So 1 times 1 is 1. So that selects for that and then gives us 2. Does that make sense? And then on and on like that. Okay. We good? Can someone simplify this?
Yeah.
Oh, you did? Huh? Okay. What's the simplification? I'm trying to decide whether it's worth simplifying or not worth simplifying. But this looks very long. I'll just leave it. Once you're done, just let me know. Okay, so now we're done with W2, W3. Cool? What we need to do now is make the add I and the mul I. Okay? So the first thing we need to do, we need to figure out where the add I is supposed to evaluate to 1. And then we'll use that to build the add I. So in this layer now, how many addition gates do we have? 1. Just 1. So that means that if you evaluate that add I over the entire Boolean hypercube, you will only get 1 at one entry. Right? While the rest of them you get 0. And what entry is that supposed to be? 0?
What entry is that? 0, 0, 0, 0, 0, 1.
Let me repeat the question. Yes, that's correct. So I'm saying that we want to be the add and mul MLE, right? For this layer. Sorry. For this layer. Now, how many addition? Okay, wait. How many addition gates do we have? 1, right? So that means that there's only one combination of outputs left and right that should give us 1. What combination is that? Yes, right? A is 0. B is 0, 0, and C is 0, 1. This is the only combination that should give us 1. Any other thing should give us 0. Make sense? So with this, we can build the polynomial that actually encompasses this. Yeah, what's the...
1 plus
Did you verify this? Because it was wrong. Everything will be wrong. Okay, but just call it. 1 plus 2x1 plus x2. Is that all? Yes. Oh, nice.
Sorry. This polynomial now
yes.
is representing the entire W3.
Yes. So we can test it, right? Let's evaluate it as 0.
Sorry, just hold on. So it's representing the entire W. What is W3 again? Okay, it's representing the entire W3. While the other one is representing the entire W2. Everything.
Let's test, right?
Okay.
So let's say W3, right? Evaluated as 0, 0 is supposed to give us what? 1.
Yeah.
So you can see it, right? That would be like 1 plus 0 plus 0, right? Which was 1. Then let's say 0, 1, right? That would be 1 plus 2 times 0, right? Plus 1. Now 1, 1, that would be 1 plus 2 plus... No, 1, 1 was the last one. 1, 0 is what I'm supposed to do now. So this will be 0, right? Which is equal to 3. And 1, 1 is going to be 1 plus 2 plus 1, which is equal to 4. So it's correct then. We just tested it against everything. Does it make sense? Yeah. So this is just encoding the data on that layer. and encoding data on the other layer, and encoding data on the other layer. This is just the W polynomial. Now let's build the add. Okay?
I want to. So this interpolation you did now.
You don't need to do it when you're coding.
If we don't need to do it, like I don't know. I'm trying to. How are we going to do it?
No. So, so this is coefficient form, right?
Yes, this is coefficient form.
You already have a multilinear polynomial that works in evaluation form.
Okay.
So when you are creating this W3, you are just creating.
You have to keep it in evaluation form.
Yeah, which is already in. Multilinear poly dot or new. I don't know how you did yours, right? There's now be like 1, 2, 3, 4. This is your own version of W3.
Okay.
Then you cannot evaluate it anywhere you want to evaluate it. But then I don't want to be doing this by hand and doing linear interpolate and doing pairing and doing all those things. So that's why I am interpolating myself. Does it make sense?
Yes. That 1, 2, 3, 4 is like the evaluation
form of this. Exactly. This is why we taught you guys evaluation form. Because of GKR gives you the evaluation straight up. So if we're doing coefficient form, then you have to do like an interpolation step, which is expensive. But now you can just take it in as like the evaluations and then you're done. You get?
Yeah.
So now we have our W2, W3. Let's make our add I. So the add I is only going to evaluate to 1 at a certain location, right? Which is 0, 0, 0, 0, 1, right? 0, 0, 0, 0, 1. That should give us what? 1. Now these are many variables.
5.
The first one is A, right?
Why is it only from 3 to 5?
It's only from...
Why is it separate the 0, 0, and 0, 1?
Because of... It's technically 2 bits. You won't just pack it as like 1. It's 2 bits. This is like a multilinear polynomial in 2 variables. And this is a multilinear polynomial in 1 variable. But then you're using 2 parts from this, right? So that's 2, 2, then 1. This is what this is like, I was saying like the GKR, the polynomial might look like it's just FABC. Like the entire GKR, they just call it FBC. Like that's all, like regardless of how many layers you have. But that B and that C can have like up to 100 variables inside. B1, B2, B3, B4, B5, up to B100. And C1, C2, C3. So it's just like, when you're actually doing the polynomial implementation, sorry, you actually use it. Alright. Let's continue. So,
So this stuff we did here now, we just assumed
that what?
That this is going to give us 1.
It's not assuming, you know. We looked at the circuit.
Yes.
And we saw that this is the only add gate on this layer.
So the reason why I say we assume is because we looked at the circuit.
Yes.
I was thinking maybe
how
we're
it
going to have something that is going to check that plus for us.
No, when you are writing your circuit,
Yes.
you are writing this. Like when you are, the process of constructing a circuit is basically similar to the process of building your adder and your multiplier.
Okay, so now we are just taking that.
So now we're like taking it here.
Okay, assuming that we are working.
Yeah. Makes sense?
Yes.
Okay. So this layer now has A as 1 bit, right? It has B as 2 bits and it has C as 2 bits. So I'll call this one A1, B1, B2, C1, C2. Makes sense?
Yeah.
So now I'm saying that this should give me 1 when A1 is 0. What does that mean? 1 minus A1. Right? Check 0 for A1. Then,
I'm trying to get polynomial.
yeah, I'm trying to get polynomial. 1 minus B1. Oh my god. 1 minus B2. 1 minus C1. C2. Right? This is the polynomial that when you pass this in, you will get 1. But if you pass in any other thing, you will get 0. So this is a... Sure. 5 variables. Based on the circuits.
I understand that part.
Based on the circuit, A is 1, right?
Yes.
And B is 2, and C is 2, right? Yes. Okay. So the first one will go to A, then the next two will go to B, and next two will go to C. So it's exactly the same idea as like check 0, check 1. We're saying that this should evaluate to 1 when A is 0, and B1 is 0, right? So we check 0 for what? A1. Does it make sense?
Yes.
Do you get this now?
Yes.
Okay. And then 0 for B1, and then 0 for B2, and then 0 for C1, and then 1 for C2. So this is the add IMLE. Like this is the full add IMLE. The reason being multilinear extension. That's like, so no, normally now, right? How it's supposed to happen is that we're supposed to have entries for all values, right? So 0, 0, 0, 0, 0, 0, right? 1, 2, 3, 4, 5. This one is supposed to be equal to 0, right? Then we're supposed to have the same thing for 0, 0, 0, 0, 1, right? This is one that is equal to 1, right? And we're supposed to have for 0, 0, 0, 1, 0. This is going to be 0. And we're supposed to continue this until we have for 1, 1, 1, 1, 1. And that's supposed to be equal to 0. But then, the way it happens is that we multiply the evaluation by the thing that we check for, right? And since all the rest are 0, then we can just ignore them and just focus on the one that's actually 1. So if you did it this way, you will still get this. Does that make sense? If we had 2 addition gates, that means we'll have like a plus here with the second one in here. Does it make sense? Yes. Okay. So that is our add-I. Then more. Someone is working on that. When it's done. But this one might not be simplified because this one will be larger. This one will be larger when we simplify it. Yes. Because there's no cancellation, there's no shared variable that will cancel each other. I'm trying to create a polynomial. Technically, we don't need to. That's right. We could just like leave it as add, right? And then see based on the place we're evaluating whether it's 0 or 1, and then just replace it. Yeah, I think we'll probably do that because that might be neater because rather than trying to multiply it all through and everything. But let's do more now. How many more gates do we have? What's the location? 1, 1, 1. So 1, 1, 0, 1, 1, 1. Right? Right? Yeah, that's passive in interview.
I don't know what's going on.
Let's continue. So A1, B1, B2, right? C1, C2. Same idea, right? A1, B1, 1 minus B2, C1, C2. Now these are our mall ABC, And this is our add. So we have everything we need now. We can now construct a polynomial that relates W2 to W3. But it never looks into that W2 polynomial, right? It will only get whatever it wants to get from just the W3.
What you said previously about coefficient and evaluation functions. So let's do a programming now. One of these coefficients that we want to see.
You will have like a vec, for example, of all zeros except for the location that is supposed to be a 1. Do you get? You say you will get it. So this number now, right? It's an actual decimal number. Like let me see, 11011 to decimal. That's 27. Now what's the maximum? That's 111, right? That's 31. So you have an array of 32 zeros initially. Then all the places that adder is supposed to evaluate to 1, you just change it to 1. So like that's 27. You index the array at 27 and you just change it to 1.
Who had put this
You would define your circuits. Then once you define your circuits can now generate the add I, the mul I, and then the W's and everything. But implementation detail. Your implementation is going to, you guys are going to go back to polynomials. You are going to add a new type of polynomial. You are going to go back to sum check. You are going to modify your sum check to work with GKR before you now even start doing GKR. Not really. You can create one sum check. Depends on how you want to do it. Well, it is long. That's why I need you guys to be done with your sum check. Let us review it. Let us review your multilinear polynomial before you guys now embark on this journey. But if you guys survive it, you will survive almost anything. Well, if you survive GKR, this is where people they will run.
It's not just stop, you run.
This is where they will run. This is where you run. Like it's so you don't have to calm down and just.
Are you a bit stupid now?
No. You guys submitted this thing first.
What's the rationale behind using x1, x2 to interpolate and using?
Don't mind me.
No. I'm using like
A.
0, 0, 0, 0, 1, for example. Like using two variables to represent
the W.
Yeah, and then using two variables and using 4 variables.
What do you mean 4? 5? The
Yeah,
add is 5, right?
And then using 5.
Yes. So if you look at that equation, the actual equation, right? See this. The add has X, B, C. But the mul has the W just has one variable. So it's built into the structure. The add is supposed to have more variables than the W polynomial. Those are supposed to have just like the length of the bits in the next layer. Does it make sense? But then you should now start seeing that there's a relationship between these two. So I'm supposed to name them properly. I'll do that after. Does it make sense so far? W2, W3, add more.
Yes.
Cool?
Yeah.
So now we should be able to combine this.
We didn't do add more for W2, it's W3.
No, we did for
We did
W2.
for W2. Previous one.
This is W2 now.
See, this is W2.
Yes.
There's only one add gate.
Okay.
Hence why there's only one point where it should be equal to 1.
Okay.
And there's also only one mul gate. And remember that this first variable in the mul represents the output. And if you look at W2, Label 1 is multiplication.
W2 is where we are supposed to have three variables now.
What do you mean 3 variables?
0, 1, and the output.
That is when it's relating to
This is the,
Yes, now.
we're relating W2 to W3.
Oh, okay, not.
Yes. That one will have not been like this. Alright? So your add will just have like add I A B C.
Please, can you slow down? When did you interpolate W2? Here, that has got 9,
Yes.
9x plus 3.
Yes.
And that is where W2 ended.
Yes.
You don't need the add for it.
That's what we created here.
For the W2.
Yes.
Yeah?
So we still add them together.
For the, okay. So this add is a relationship between W3 and W2. So we are picking the value of W3 first. That's what's making the A.
Value of W2 first.
Yeah?
It's value of W2 first. You know the add is like output left, right.
Yes.
Output is going to come from W2.
That's what I'm saying now.
You
So
said,
the
okay.
value of W2, that's
miscommunication,
what is
yeah.
representing the A.
The value of W,
2, like
the label.
yes, that's what it's presenting A now.
Yes.
Then the rest is from W3. That's the
Left
the left
and
and
right.
of W3.
Yes. Is it making sense?
It always makes sense in class, right?
There are two parts: understanding the theory and then figuring out how to implement it. Those are two different problems.
So sorry, go back to the diagram.
Okay.
So that polynomial we got now covers everything.
Which polynomial?
The one now that interpolation we did that we got 1 minus a into.
You mean the add I?
Both the add I and the
Small I.
And the small I.
Yes.
You know we are supposed to add the both of them together.
Yeah, that was the next step. Yeah, that is the next step.
Where we add them together, the resulting polynomial covers for everything.
Yes.
On W3 related
On
to
W2. Yes. So if I evaluate that combined polynomial
Yes.
at 0,
Yes.
we'll get 3.
At what?
0.
At 0, we'll get 3.
Yes. And if I evaluate it at 1,
Okay,
we'll get
yes,
12.
We'll get 12.
Yeah. But then the formula is not going to have W2 inside at all. So it's going to be gotten entirely from W3.
But when you evaluate it, you give
You
it
still
as
get the
add
answers
I.
of W2. So it's like a different way of representing W2, but representing it just with W3.
Oh, so now the verifier with that polynomial can now assert that okay, the values from W. No,
You know?
what we are saying is if W2 is correct,
Yeah.
actually the output is correct.
Yes. If there's a claim about the output, right?
Yes.
And then reduce it to a claim about W2.
Yes.
Now you're trying to reduce it to a claim about W3.
W3.
Yeah.
So if he gets a polynomial at W3
Yeah.
and he's able to get the values at
W2.
W2, he can get the output.
You are going the other way.
Yeah?
You are going the other way.
Okay, let's not go to that.
But if this is correct, Sha,
Yes.
it means the top was correct.
Yes.
And if that one was correct, then it means the original was correct. So
Is there a way
to go up
to carry up to W?
from what to what?
You know, the verifier knows the output.
If I is told the output by the
Knows the
prover,
output.
an
It's not
untrusted
sure,
output, yes.
Right?
Yes.
So the output now is reduced to W2.
Yes.
Right.
So you now have a new claim about W2. W2 of something is equal to blah blah blah.
Okay, you know we didn't do the reduction to W2.
Yeah, because I was like, it's the same reduction.
Yeah?
It's exactly the same reduction process. But I'm trying to show it for something more interesting. Like what I've done here is exactly the same thing you do when you're doing the W1 to W2, right? But you still create your W1 polynomial. You still create your W2 polynomial. Then you still create your add and your mol. But in this case, there's just one add. There's no more.
Okay, so you know, slow down a bit.
What do you want?
Yeah, this 9x plus 3. That's the polynomial for W2, right?
Yeah.
Are you saying if we do the same thing for the output, like we reduce the output down, we'll still get back this polynomial?
What do you mean?
You know, normally we are trying to reduce the higher step to the lower step, right?
Yes, eventually they claim about a higher step to the lower step.
So now we didn't do from the output to W2, right? We just did from W2 to W3. We have seen.
I've not yet seen.
Okay.
We're in process of seeing.
We'll see.
Right. Hopefully.
Now, what I'm saying is the reduction from the output to W2 is what, okay, let's just finish, then maybe we can do the reduction from output to W2.
Yeah.
But if that polynomial you got from interpolating those values at W2, this 9, I'm thinking that if we reduce the value, the output to W2, we should get the same polynomial.
No, but the thing is that you're not trying to get the W2 polynomial with W1. You're trying to get the W2 polynomial with W3. And you're trying to get the W1 polynomial with W2. You see the way the equation is going up.
Okay.
Right? So it's this input that will give you this, not the other way around.
Okay,
so what we're creating now is a formula that uses W3 to give you back W2.
Slow down, let me see something. Down. Okay, this okay. So if we want to get what this stuff we'll get is like the W3 that gives us W2 now. So if we want to get the W2 that gives us the output, we'll do something like, you know, the output is at 0. So it's going to be like at 0, 0, 1.
That will be the add I. That's the point where if you evaluate the add I at, it should give you 1, right?
Yes.
For the first 2 layers. Yes.
So it will be
add 0, 0, 1 is equal to 1.
0, 1. And that's all now.
And that's all, yeah. For that layer. But for our layer, we add 2, right? Yeah.
So the mol will just be 0.
The mol is 0. So now let's build that function that we're going to run some check over. Okay? What we could do is that we could actually do the full reduction so that we can get back W2. So we can get back this. I think that would be something that might be useful.
Okay, that interpolation you did first to get 9x plus 3 is just to show us the W2 equation. So you want to reduce this guy to get back that guy.
Okay. Initially, I just wanted to do it by evaluating the guy at the bottom at 0 and at 1, then showing you that the answer is going to be 3 and 12. We'll do that first. But you could technically use algebra and do full reduction until you get 9x plus 3 at the end of the day. So we'll see, we might do that. But let's continue now. So now we have our add I, we have our mol I, we have W3, right? That's all we technically need to be able to create W2, right? So W2 evaluated at any x, I should stop calling this x now. I start calling it A, alright? W2 evaluated at A is equal to the sum, right, of B, C in 0, 1 to 4, right? of, now add times the addition, right? What's our add? This really large formula. 1 minus a1, 1 minus b1. So now this is actually, let me write it out properly. b1, b2, c1, c2 in 0, 1 to the 4, right? So if it's 0, 0, 0, b1 will be 0, b2 will be 0, c1 will be 0, c2 will be 0. If it's 0, 0, 1, b1, b2, c1 are all zeros, then c2 is going to be 1. Does that make sense? So, and then we now have like 1 minus b2, 1 minus c1, c2 times, that's the add I. Yeah.
So writing out 0, 1 minus 0, 1. Can't just put either.
If it's up writing out,
Can't just put add ABC.
rather than writing it out, I could.
So just
I like pen. Yeah. So now we have the add I, right? This technically is like the add I. Then once we have the add I, we're supposed to multiply it with the W3 evaluated at B1, B2, the left, plus W3 evaluated at C1, C2. So this is going to be what? W3 evaluated at B1, B2. Remember that B means left. So we're actually getting the concrete left value. Then we're adding it with, do you get? That's the add side of things. But we're not done. We're not supposed to do plus the mul side of things. What was the mul I? A1, B1, 1 minus B2, C1, C2 times W3, B1, B2 times W3, B1, no, C1, C2. This is the full equation. My claim is that if you simplify this, you will get 9x plus 3. You get 9x plus 3.
What's next again?
Yes, 9a plus 3, sorry. If you fully simplify this, you get 9a plus 3. So, but now look at this. We're saying that W2 evaluated anywhere is equal to something that is only in W3. Can you see that? So this doesn't have W2 in it anymore. So it's not cheating. This is like legitimately another way of getting any evaluation in W2. And it looks like a sum check equation, right? So the prover is actually going to say, oh, W2 evaluated at 10 is equal to 15, right? So we're not going to say, oh, okay, 15 can be here, right? But A will now be what, 10. So we'll put 15 here. Sorry, people that are watching this will not know where year is. We'll put 15 here, and then we'll replace A with 10, right?
Sorry.
A as 10. Is it 10? 15 is like the total sum at the top, right?
Yeah, the prover said that W2 of 10 is equal to 15, right? That's a claim about W2. But now, we already have another way of getting W2 evaluated somewhere, right? So we'll just replace this with 15. You said it's 15, right? Exactly. And then wherever it is A, we replace it with what? 10. So we replace here with 10 and here with 10. I don't know why I call it A1. It should not be A. So now once we now do that, we can now run sum check, right? When we are done running sum check, we'll now get, oh, this is long. This is crazy. This is crazy. When we are done running some check, we will now get like R1 and R2, R1, R2, R3, R4 for B1, B2, B3, B4. B1, B2, C1, C2. We'll get random challenges for them, for the 4 of them. So you're not supposed to make a final oracle check on this thing that is inside with R1, R2, R3, R4. It's all what? B?
What do you expect on the premium number? 1 minus B1, blah, blah, blah. I think that's the add up.
Yeah, that was first one the add.
I think as I estimate, it's like 1 or 0.
Yeah, it's still 1 or 0.
It's still 1 or 0.
Yeah. This will only evaluate to 1 when you have like 0, 0. We did it here. Like, see this now. So this is the only time it's going to evaluate to a 1. When the input is 0, 0, 0, 0, 1. If you check for any other Boolean combination, it will be 0. But then if you check for anything outside Boolean, then that's when you might not get another field element. Yeah. Does this make sense? Let's actually evaluate it at 0 and see if we get 3. Right? Cool? So we're saying W2 of what? Right? Okay. So we're going to sum. Hey.
It will be much.
It will be a lot.
2 raised to power 4.
Okay. So what I'll just do is like, rather than writing it, I'll replace it with add I and more like, so that it's like a lot easier. So this add I of, this has been fixed to 0, right? The A has been fixed to 0. Then B1, B2, C1, C2, right? Then times W3 of B1, B2 plus W3 of C1, C2. Cool? Then plus mol I of fixed also, right? B1, B2, C1, C2. Then W3 of what? B1, B2 times W3 of what? C1, C2. Okay? So now what we're supposed to do is we're supposed to go over. So there's no longer A, right? I remember that we just did B over 0, 1, 4. Okay? So I'm going to try every possible combination of 4 values. And I'm going to replace B1, B2, C1, C4 with those 4 values. Cool? Now, the only way this thing would not be 0 is if we get the combination that will make add I a 1 or mol I a 1. So we can ignore the other ones just so that it's not too much work. Does that make sense? But let's just see for like, if it was 0, if we started at the beginning, B1 will be 0, B2 will be 0, C1 will be 0, C2 will be 0, right? Neither add
So
I.
can you be relating them with diagram so that we see?
Which diagram? The diagram was. Wait. Let me finish this. We're summing this over the Boolean hypercube, right? For B1, B2, C1, C2. Cool? Now, the first entry in the Boolean hypercube is 0, 0, 0, 0, right? Now, if we put 0, 0, 0, we'll now have add I 0, 0, 0, 0, 0, right? If you look at all the possible add I's that are valid, that does not exist, right?
Yeah.
Right?
Yeah, it's going to give 0.
It's going to give 0. And neither does mol I have something like all zeros, right?
Yeah.
So that means that this will turn to 0, this will turn to 0. And it's all multiplication, right? So everything will turn to 0. So only the places where mol I and add I give 1, those are the only places we need to actually check, right? So at some point, while the for loop At some point, while the for loop is iterating over all possible combinations of B1, B2, B3, B4, and B1, B2, C1, C2, it's going to hit upon 0, 0, 0, 1, right? It's going to hit upon 0, 0, 0, 1. Then at some point, again, it's going to hit upon 1, 0, 1, 1. Okay, but you know we're evaluating at 0.
Yeah.
So the more will never trigger. Why? Because more starts with 1. Does that make sense? So more will never trigger. So the only thing that will trigger is add. And add will only trigger when the 4 bits are 0, 0, 0, 1. Does that make sense? So when we get this 0, 0, 0, 1, we're now going to do what? Add I, 0, fixed. Then B1 takes from this. B2 takes the next. This one takes, and this one takes, right? Then times W3. What's B1? 0, right? What's B2? 0. Then what's C1? What's C2? Okay? So once B1, B2, C1, C2 hits this, we'll have this, right? The more will be 0, right? Because it starts with. So now what's this? This evaluates to what?
1.
Then what's W300? So now we're going to check our W300. That's what?
1.
So replace this with what? 1. What's W301?
2.
So replace this with 2. So basically that's like 1 times 3, which is equal to 3. Which is exactly the same thing as W2 evaluated at. Does it make sense? Now let's say I wanted to do W2 evaluated at 1. The only thing that will make either the add or the more, so like add will never trigger, right? Because of it always starts with 0.
0, yeah.
But more will trigger when B1, B2, C1, C2 is 1, 0, 1, 1, right? So it's going to be 1, 0, 1, 1. This is what will cause a trigger. So add, we'll forget about the add side. Then we just do more I. The 1 was already fixed, right? And then it's now going to be 1, 0, 1, 1. Then times W3 of B1 is what? 1. And B2 is 0. Then times, right? W3 of B1 is what?
1.
And B2. So this is 1, 0, 1, 1. So we're trying all possible values of B1, B2, C1, C2 over the entire Boolean hypercube. And we're evaluating this, our formula here. Right? But rather than doing everything by hand, we're figuring out the place where this thing will actually not be 0. Okay? So since we've already fixed 1 here, it means that the only place that it's not be 0 is where small I sees 1, 0, 1, 1 coming after. Yes. Does that make sense? So once it has been like it's searching, once it gets to 1, 0, 1, 1, then mul would trigger as 1, right? Then that's why this is 1. That's what we did earlier. No. So look at the add. The mul can never trigger when A is 0, right? Because there's no mul equation that starts with a 0. But there's an add equation that starts with a 0. But it will only trigger when the rest of them are 0, 0, 0, 1. Does that make sense? So that's why we now used 0, 0, 0, 1 here. So then this one is the B1, B2. That's why they went here. And this is the C1, C2. That's why they went here. So all we just need to do is now check what the actual values are in the circuit and then do the addition.
Sorry, so if that add was in, if say we had like 4 layers and add was like, and one of the add was like 0, 1, that means that the first byte that you left out as the first one.
The one that was fixed.
Yeah, that was fixed.
Will be 2 bits.
Will not be 2 bits.
Yeah.
So that means we are now going to check for the first 2 bits to check if it's for add or for multiplication.
You partially evaluate the first 2 bits, so those ones will be out. Then you're just like summing over the Boolean hypercube with the remaining bits.
Yeah, because what I'm actually is I was actually not in for the last 10 minutes or so. So it's kind of like I'm trying to.
I'll send you video link. You'll watch it. So, W3, right? This makes sense up to this point, right?
Yeah.
So W3 of 1, 0 is what? It's 3, right? And 1, 1 will be 4. So that will be like 3 times 4, which is 1 times 12, which is 12. So you can see that we're able to get both our 3 and our 12. And if you're ambitious, you can simplify this formula. Like really simplify it. So that you can see that it's reduced to this. That's my point. When you fully simplify that, it's going to reduce to 9a plus 3. Because it's supposed to be equal to W2.
Okay, and then it will be
Yes.
0 plus 3 and then 9 plus 3. Ah,
Interesting.
at 0 and 1, right?
Interesting, yes.
That's 3 and 2.
2 and 12, exactly. They're exactly the same, but they're gotten in 2 different ways.
So when you say with simplify, can I see that equation?
Eventually, you can just
Which of them? The one below or
The one above.
so we have fixed values for B and C already.
No, B and C will be evaluated over the Boolean hypercube.
Sorry, that write-up, is it white or yellow?
That what?
The write-up on that screen.
Are you seeing double?
Honestly, I had to look on my phone to be sure that it's white.
You need to sleep.
No, actually, it's not pure white. No.
Off-white.
So it's kind of like off-white.
Okay, it's the screen. But yeah, it's white. Pure white.
So don't be my eye.
I like it.
No, be right. Does it make sense?
Yeah, probably.
So you understand the relationship between 2 layers.
Can we be any plan by that will have enough time
Becoming early now.
Yeah?
Becoming early.
Yeah.
If we come by 9 on the dot, like 9 on the dot, we'll end by 2.
I come here before 9.
And that's you. That's you. I'm laughing at you. So now let us write it in a way that abstracts everything. Because when you're actually analyzing the algorithm, you should not be thinking in too much details like this, right? So instead, what you want to do is like you want W, I, so it's more something like this, right? Like that long polynomial that we created is just FBC, evaluated at, let me call it A. Evaluated at A already. Or you can write it like this. Right? Where the A is already fixed based on the A coming here. And then B and C is now like you sum over the Boolean hypercube. But the way we actually write it is like this. Right? It's just like partially evaluated at A. So then B and C are just summing over the Boolean hypercube. So this is how you should like maybe be reasoning about it. So in GKR, every round, you're supposed to get the FBC polynomial for that round, which is FBC polynomial for that round. And this FBC polynomial, fa of b comma c, is equal to add I of a comma b comma c times w I plus 1 of b plus w I plus 1 of c, then plus small I of a comma b comma c times w I plus 1 of b times w I plus 1 of c. Does it make sense?
Yes.
So now this b now might actually be b1, b2, b3, b4, but that has been collapsed. But now you can reason about like the GKR protocol this way. So you get your FBC polynomial every round, which is this, and then you run some check on this polynomial every round.
You didn't specify the
I.
size of the tuple.
Yes, I didn't specify it. It depends on the layer.
Shouldn't there be like a superscript x or something like that?
And you can make a superscript x where x is equal to log base 2 of like wi.len or something. Yeah.
So, are there still...
Yes. I've not done anything.
That's
This one is
that's
just...
the explanation
Yes.
on GKR.
Yes. Well, I've not... This is like... We're now at... Let me see the percentage.
We're starting with 30%.
Yeah, wait, let me see. You still have to do like the double sum check, then wait, it's 49. Then the combination. Oh, that's yeah, like 49.50. 49.50. But don't worry, the way we'll do it right, we're going to break it down into like milestones, right? So the first thing you need to do is you need to build your circuit. I need to be able to express your circuit. That one is independent of lots of like the GKR program and everything. So your first goal will be to build a circuit representation and be able to generate that's like output, yes. So someone will give you the input and you'll be able to run the inputs through and get the intermediate like W's, right? And get the outputs, right? And then you should be able to generate your add I, MLE, and your molar MLE for different layers. That one, you guys already have like the theory behind that. So we might now do like a design session on how maybe you might implement that. So once you're now done with the circuit, then that's where trouble starts. You guys now start going back and bruh. Even me, I'm like
Even you say put your hand on the head. Like,
Well, you said something that when we start GKR, that we are going to know where to go back to.
I mean like your sum check and your
Our subject approach.
it's not now that you see
Not
that.
now we see
It's when you start looking at the proving. That's when you see that. So what we want to do now, you guys will go on a break. Then when you come back, we'll now do the design session.
Today?
Yes, today. For the
Sorry,
for the
today?
circuit.
For the circuit?
Yes. You guys do the design session for the circuit.
How many hours break?
Come back by by 1:16. So 30 minutes. You want to say something? 1:30. You want to give them more time? Oh yeah, 1:30. Thanks, Francis.